Hi, this is your video for section 8.2 about the sampling distribution of a proportion. First, let's talk about sampling distributions. The sampling distribution of a statistic, such as the sample mean or sample proportion, is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. What we're going to talk about in this section specifically is sample proportions. So suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. We can think of this as a binomial experiment with n trials, where having the characteristic is considered a success. The sample proportion, denoted p hat, is given by p hat equals x over n, where x is the number of individuals in the sample with the specified characteristic. Again, if we're thinking of this as a binomial experiment, remember x would be the number of successes. The sample proportion is a statistic that estimates the population proportion p. Since the statistic is a single number, a point, we call it a point estimate for the population proportion. Now let's talk about the distribution of sample proportions. Remember, we're talking about all possible samples of size n from a particular population. So the sampling distribution of the proportion is the distribution of sample proportions with all samples having the same sample size n taken from the same population. Sample proportions target the value of the population proportion. That is, the mean or expected value of the sample proportions is equal to the population proportion. The distribution of the sample proportions tends to be a normal distribution. Here's an example. According to a poll conducted last month, 42% of registered voters plan to vote for the incumbent in the upcoming election for the state legislature. Describe the sampling distribution of the sample proportion for samples of size n equals 10, samples of size n equals 50, and samples of size n equals 100. Now, the results on the following slides were obtained using simulations instead of real samples. So here are the results from 300 simulated samples of size 10. And remember that what we're talking about is the distribution of the sample proportions. In other words, if we had these 300 samples of size 10, for each sample we would calculate the sample proportion. In other words, the proportion of those surveyed who plan to vote for the incumbent. We would take all those sample proportions from all those different samples, and this is what the distribution of those sample proportions looks like. If we look at the highest bar in this histogram, it's between 0.2 and 0.3, which means that a lot of our sample proportions were somewhere between 0.2 and 0.3, or between 20% and 30%. If we look down here, this is the mean of all those sample proportions, is 0.426, and this is the standard deviation of those sample proportions, is 0.160. Here are the results from 300 simulated samples of size 50. So here we have samples of size 50 instead of size 10, but we're still doing the same thing. For each sample, we're finding the sample proportion, and then this distribution shows us what all those sample proportions look like. So in this one, the highest bar looks like it's between 0.35 and 0.4. The next highest is between 0.45 and 0.5. Notice that the majority of our sample proportions are between 0.35 and 0.5. Our mean for this, again, is 0.426. The standard deviation is 0.072. It's a little bit smaller than the standard deviation for our samples of size 10 because that was 0.160. Now here are the results from 300 simulated samples of size 100. So we've doubled the sample size from our samples of size 50. Our mean for this one is 0.42. So here's our mean, which is also where our highest bar is, right here in the middle. And notice how many of our values are grouped around that mean. Also in this one, our standard deviation is down to 0.047. It's a little bit more than half of what it was for the samples of size 50. So if you compare the three graphs, what's happening is that our standard deviation keeps getting smaller, which means our values are more closely grouped around the mean. So here was the last one, which was a little bit more spread out, and for the samples of size 10, it was even more spread out. So here's some key concepts that have to do with our distribution of our sample proportions. First of all, the shape. As the size of the sample n increases, the shape of the sampling distribution of the sample proportion becomes approximately normal. So in those three histograms we had, as our n kept getting bigger, our histogram looked more bell-shaped, looked more like a normal distribution. The next thing we can talk about is the center of the distribution. So the mean of the sampling distribution equals the population proportion P. And in all three of our histograms, all three of our examples that we had, the mean was fairly close to 0.42 or 0.43. The third thing is the spread or the dispersion, and this has to do with the standard deviation. So the standard deviation decreases or gets smaller as the sample size n increases. And that's what we saw as our sample sizes got bigger. So our sampling distribution of p hat, which is our sample proportions. For a simple random sample of size n with population proportion p, first of all, the shape of the sampling distribution is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. This is a condition that we need to verify so that we know our sampling distribution is approximately normal. The mean of our sampling distribution is p, which is our population proportion. And notice our notation for this. It's the mu, which stands for the mean, but it has a subscript of p hat so that we know we're talking about the mean of the sample proportions. The standard deviation of the sampling distribution is this. So we have the square root of p times 1 minus p all divided by n. And again, our notation, this Greek letter sigma stands for the standard deviation, and it has the p hat as a subscript, so we know we're talking about the standard deviation for the sample proportions. One more condition that we sometimes need to verify, if we're sampling from a finite population, then we have to check whether our requirement for independent trials is needed or not. And to do that, we need to know that the sample size n is no more than 5% of the population size. So we can just check that n is less than or equal to 0.05 times our population size. Let's go back to our example. So in this one, because of the poll conducted last month, we're assuming that our population proportion P is 0.42. So let's suppose that we obtain a simple random sample of 50 voters and determine which voters plan to vote for the incumbent, so we know how many successes we have in our sample. Then we would want to describe the sampling distribution of the sample proportion for registered voters who plan to vote for the incumbent. First, let's check our assumptions. First of all, the sample size of n equals 50 is smaller than 5% of the population size, which would be all registered voters in the district or the population we're talking about. And this would assume that there are at least 1,000 registered voters in the district. The other assumption that we need to check is that n times p times 1 minus p is greater than or equal to 10. So our n was 50, our p is 0.42, and then 1 minus p is 1 minus 0.42. If we multiply those together, we get 12.18. So that is greater than or equal to 10. So to describe our sampling distribution, it's going to be approximately normal since these two assumptions were verified. Our mean is the same as our p that we had, which was 0.42, and our standard deviation, we use that formula, so we have the square root of 0.42 times 1 minus 0.42 divided by 50. So our standard deviation turns out to be 0.0698. And remember, in the examples that we saw from the simulations, this standard deviation comes fairly close to the one that we had for the samples of size 50, which was 0.072. This turns out to be 0.0698, so it's not too far off. Now, how do we find probabilities for a sample proportion? Well, first we want to verify our assumptions. So this one, that np times 1 minus p is greater than or equal to 10. And if the population is finite, that n is less than or equal to 5% of the population size. If we can verify those two assumptions, then we can assume that our distribution is approximately normal. If we're going to think of it as a normal distribution, we need the mean and the standard deviation. So we use these two formulas. The mean is just our population proportion. The standard deviation, we use this formula. So now we just have a normal distribution. We know the mean and the standard deviation. So we're going to find the probability using the same methods we did in Chapter 7 for a normal distribution. Here's an example. We're going to use the same example we have been. Using that, we want to find the probability that out of a random sample of 50 registered voters, at least 50% of those surveyed plan to vote for the incumbent. So we already checked our assumptions, and we calculated the mean as being 0.42 and the standard deviation as being 0.0698. So we have a normal distribution with this mean and the standard deviation. And we want to find the probability that the sample proportion, p hat, is at least 50%, or 0.50. In symbols, we have probability of p hat is greater than or equal to 0.5. So we're going to draw our picture of our normal distribution. So here's our picture. Here's our mean in the middle is 0.42. And if we take that and go up one standard deviation, we get up to 0.4898. So our 0.5 is just a little bit above that. Since we're finding the probability that it's at least 50%, we're going to shade from there to the right. And then we want to use our normal CDF on our calculator. So our lower bound is going to be the 0.5. Our upper bound, we can just make a big positive number. Here's our mean of 0.42 and our standard deviation of 0.0698. And on the calculator, the result of this would be a probability of 0.1259. So the probability that at least 50% of those surveyed plan to vote for the incumbent is 0.1259.